The past few months, we've begun to see glimpses of AI systems improving themselves.
Hey, are live demos
Hey.
risky?
Live demos can be risky, yes. They can be unpredictable.
A machine that can think with confidence sounds unusual, right? Yet that's exactly what researchers from Meta AI and UC San Diego have achieved. Their new method, called DeepConf, has just pushed large language models to human-level reasoning benchmarks with almost perfect accuracy while cutting down the heavy costs of computation. Why reasoning has always been expensive? Large language models, or LLMs, are the engines behind today's most advanced AI. They can solve complex math, explain concepts, and tackle logic problems. But when it comes to reasoning, the standard approach has always been costly. Methods like self-consistency and chain of thought work by generating multiple solution paths. The idea is to create many traces and then pick the most common answer. Accuracy does go up, but only for a while. The problem is that producing more traces doesn't guarantee better results. Low-quality reasoning often sneaks in and dilutes the majority vote. Even worse, this approach burns through huge numbers of tokens. Each token costs compute, time, and energy. Generating hundreds of long traces for a single question makes reasoning both expensive and inefficient. That trade-off accuracy at the price of cost has held back AI from scaling into practical, everyday use. The DeepConf insight, the team at Meta AI and UC San Diego realized that not every reasoning trace is equal. Some are reliable, while others show early signs of collapse. The key was to make the model itself aware of which paths were strong and which weren't. DeepConf, short for Deep Think with Confidence, does exactly that. It taps into the model's internal confidence signals and uses them to decide whether a reasoning trace should continue, count more heavily in the final decision, or be discarded altogether. This may sound simple, but it flips the reasoning process on its head. Instead of blindly generating massive amounts of text and voting at the end, DeepConf listens to the model's self-assessment during the reasoning process. If a trace looks weak, it's filtered out early. If it holds steady with high confidence, it gets more weight. By combining these signals, DeepConf manages to save enormous amounts of computation while also producing more accurate results. How confidence becomes a guide. DeepConf measures confidence in several ways, giving it a detailed picture of reasoning quality. At the token level, it calculates confidence using the negative average log probability of the top choices. This local measure catches uncertainty as the model writes. Then it averages confidence across sliding windows of 2048 tokens, creating what's called group confidence. That smooths out noise and highlights larger patterns. There are also targeted measures. Tail confidence looks at the final part of a trace, since many reasoning collapses happen right at the answer. Lowest group confidence focuses on the weakest segment in the trace. Bottom 10% group confidence goes even further, tracking the worst slices of reasoning as the best predictor of failure. By layering these metrics, DeepConf knows when to trust a path and when to stop it in its tracks. Offline versus online DeepConf. The system can work in two modes. Offline DeepConf comes after generation. The model produces a set of traces, and then the system uses confidence scores to filter or reweight them before voting. This already gives a boost, especially when using bottom 10% or tail confidence, which are better at spotting errors than simple averages. Online DeepConf is the more radical change. Here, the filtering happens during generation itself. After a short warm-up phase of initial traces, the system sets a confidence threshold. If any new trace drops below that threshold, generation stops early. That saves thousands of tokens that would otherwise be wasted. Two styles of online DeepConf balance risk and reward. DeepConf Low is aggressive, filtering at the top 10% and cutting costs dramatically, though with some risk of overconfidence. DeepConf High is more conservative, using the top 90% and ensuring stability with moderate savings. Adaptive sampling adds one more layer of efficiency, ending generation completely once a high consensus, say 95%, is reached. The benchmarks show just how powerful this approach is. At AMI 2025, one of the toughest math competitions, the open-source GPT OSS 120 billion hit 97% accuracy with standard majority voting. With DeepConf, that soared to 99.9%. Even more impressive, it achieved that result while using 84.7% fewer tokens. In other words, better performance with a fraction of the cost. Integration made easy. One of the most appealing aspects of DeepConf is that it doesn't require retraining, extra data, or months of tuning. It operates purely at inference time. For those using frameworks like VLLM, adding DeepConf is straightforward. Extending the logprobs processor to track sliding window confidence, inserting an early stop check before outputs, and passing confidence thresholds through the API are enough. That's about 50 lines of code. Once added, any OpenAI compatible endpoint can support DeepConf without further modification. Because it plugs in so easily, DeepConf makes sense for both research and production environments. Trade-offs and challenges. Like any method, DeepConf isn't perfect. One issue is overconfidence. Sometimes models generate traces that are wrong but expressed with high certainty. If filtering is too aggressive, those traces might slip through. This happened, for instance, with GPTOSS120B on HMMT 2025, where accuracy dropped under certain settings. Calibration sensitivity is another factor. The warm-up phase that sets thresholds needs to be tuned carefully. If it's off, performance can suffer, and effectiveness varies across tasks, meaning the best setup for one dataset may not transfer directly to another. Even so, the overall balance is strongly positive. The savings in computation and the accuracy gains far outweigh the risks, especially when using the more conservative DeepConf high mode. Why this breakthrough matters? The importance of DeepConf goes beyond benchmarks and numbers. It demonstrates a new way to think about scaling reasoning in large language models. Instead of brute forcing accuracy with endless computation, it uses the model's own signals to guide smarter, leaner reasoning. That changes the economics of AI deployment. Lower compute costs mean faster responses, reduced expenses, and lower energy use. It also highlights the growing power of open source models. For businesses, educators, and developers, this opens doors to high-level reasoning without being locked into closed ecosystems. Looking ahead, DeepConf could inspire further research into using confidence signals for training, reinforcement learning, and uncertainty quantification. It may even lead to systems that adapt their reasoning depth in real time, balancing accuracy and efficiency automatically. With benchmarks showing 99.9% accuracy on elite math tasks, while cutting token usage by up to 85%, this breakthrough resets expectations for what's possible in AI reasoning. And because it's open source, lightweight, and easy to deploy, its impact could spread quickly. What do you think? Are we witnessing the start of a new era where AI can reason at human levels without burning through endless compute? Let us know your thoughts in the comments.